Okay, I do want to do this. I think, you know, whoops. We introduced index notation earlier, and we introduced epsilon I, j, k. And one of the things it's really useful for is proving certain vector identities. So let's look closely. We've just seen that the curl of v should equal 0 if v equals the gradient of phi. So does anyone remember how I would write the ith component of the curl of v in epsilon I, j, k notation? Yeah, ai, bj. So what's ai in this case? That's a, it's del. So it's the jth derivative, d sub j, and then just v sub k. Now, v is grad phi. So how do I write v sub k? Yeah, that's all I do. So this is epsilon I, j, k, dj, dk, phi. Now, a key feature of partial derivatives that you recall, does it matter which order I take my partial derivative? No, it doesn't matter. So I could switch dk and dj. Okay. I have to be careful in index notation. I can't suddenly switch phi and dk. That doesn't make sense. Right? It doesn't make sense to move the derivative past the thing it's taking the derivative of. But I can switch the two derivatives. That order doesn't matter. The partials don't matter in order. So the first thing I can do is recall if I switch two indices in epsilon, what do I pick up? Negative sign. So this is negative I, kj, dj, dk, phi. Now, I just said I can do the derivatives in either order, right? So this is negative epsilon I, kj, dk, dj, phi. But now, these are just dummy indices, right? They get summed over. They can be any letter I want. So here's the trick. This is the hard thing to conceptualize about index notation. This is minus epsilon I, j, k, dj, dk of phi. Because all I've done is I change k to j and j to k. And this is important. This is not a switching of j and k. Right? If I switch j and k, what do I have to do? Pick up a minus sign. This is a renaming. Now, if I wanted to be careful, I could do this renaming in two steps. I could call k L and j m, and I could go back over there and call j L and k m. And then I could make it really clear what I was doing. But since this is the common way to do it when you're good at it, I thought I'd show you the confusing way. So notice there are two separate things I did. I switched j and k and picked up a minus sign. And you can tell that all I did was switch them because nothing happened here. I switched my derivatives, which I'm allowed to do, doesn't cost me any minus signs. And then I renamed, which I'm allowed to do, which doesn't cost me any minus signs. And why did I do that? Because now look at the beginning and the end. What did I just tell you?
It's equal to the negative.
It's equal to its negative. What is the only number equal to its negative? 0. So I've just proven that the curl of a function whose the gradient is 0. So if a function is the gradient of a scalar, its curl is 0. And I've just proven it. And it turns out this is an if and only if. So earlier we showed you that if the curl is 0, then it's a gradient of a function by using our integral theorems. Now we've shown explicitly by calculating if v is the gradient of some function, its curl is 0. And I've done it without having to actually multiply out all the components. right? You could do this brute force by writing what the gradient of phi is, and then taking the curl of it, and you would get 0. But I've done it in about 4 lines with a lot less pen.
I feel like the renaming is like strange. Like I feel like
Exactly.
why does that?
Because, and this is the key of index notation, this is what makes it so powerful, you have to fully understand what a dummy index is. I can't arbitrarily rename, because it's the ith component, and that might be relevant to something else. But k is getting summed over. It disappears when the whole thing is done. So it can be any letter you want. You just don't want it to be another letter in your expression, because that would be confusing, because then you would think you're summing over it twice. So I can't arbitrarily turn j into k without calling k something different. But any index that is summed over can fundamentally have any name I want to give it. And like I said, if I did this longhand, what I would do is turn these k's into L, these j's into M. That would be fine, right? You wouldn't care about that. That's just changing the letter. I can always change the letter. And then I would go up there, and I would change those j's into L and those k's into M. And then you would see epsilon ILM equals minus epsilon ILM, and it would be obvious. But I'm really doing this on purpose, because again, you're not going to see this on the test this year. But it's such a useful and powerful reason why we introduce index notation. And unless you see it multiple times, this step is very disturbing. And you've got to see it a bunch before you get undisturbed by it.
Do you know there's a dummy variables because you're taking the derivative?
No. There's the dummy variables because they're repeated. If this had been like a random dot product and these were not derivatives, it would still be okay. Any repeated index is just a placeholder for a sum of all those numbers. So if I were to write this out, I get a 1, 1, a 2, 2, a 3, 3. I can use any two letters, any letter I want to represent that 1, 1, 2, 2, 3, 3.
What if the original j was like 4 and had 4 terms, and the original k had 3 terms?
No, you would never do that, because that would mean you have vectors of 2 different dimensions.
So this is always a square.
Remember, you're always dealing with vectors in the same vector space when you're doing index notation.
Okay. So
Right? So they're always summed over the same thing, yeah. Because we're always doing physics. You're always doing either 3-dimensional things or 4-dimensional things.
since they have the same dimension, that when you're summing over the same number of terms, it's okay to change the index.
Well, no, keep in mind, let's just assume for some bizarre reason this only went over 2 numbers and this went over 3. They still disappear at the end. It's still a sum that disappears. So whether I call the 3 numbers j or k or p or y or z or z or rho or alpha does not matter. What I call these two does not matter, as long as I keep it as a repeated index. Right? And that's the thing to keep in mind. This j is meaningless. All this j is telling you is whatever I stick here is summed over. Let me do another example that's the same example but a different one. And like I said, I do this on purpose to force you to think about this confusing situation. Okay? Let's look at the case of taking the divergence of a vector who's the curl of another vector. Right? We just said that if the divergence of v equals 0, we can write v as the curl of a. So let's show that for any v that's the curl of another vector, its divergence is 0. So that basically what we're saying is the divergence of the curl is 0. Well, this we can write as v sub I equals epsilon I j k dj ak. The divergence is what? It's di vi. So notice here, this I matters only in the sense that it's got to be the same letter as that letter. I'm looking at the ith component. Once I get it in here, right, so let me just show you how that might work. Let's suppose I had chose to call this DLVL. Right, because I can pick any letter I want to be the letter I sum over. Then when I plug in, I have to plug in VL here, which is epsilon LJK AJ, whoops, I'm sorry, DJ AK. Because it's that letter that tells me which component I have, which is what I have there. since they're summing, they really don't matter. I don't like L's with J's, so I can write it that way. Now, this is just a constant, so I can move the derivative through. And now I see I have the same thing. I can change these two derivatives without it making a difference. But if I change I and j, I pick up a minus sign. So I'm going to get that same exact situation where this equals minus epsilon ijk di dj ak. And so I'm going to get that at 0. Now, for this one, let's just look at that for a second. What shows up in this sum? Well, d1, d2 times a sub k will show up at some point. But so will negative d2, d1 times a sub k, because that's going to show up when I've flipped I and j, and flipping I and j picks up a minus sign, right? So you can see here, I'm going to get the 1, 2, and then when I get the 2, 1, there's going to be a minus sign for my epsilon 2, 1. Here to here? Oh no, this I did it all in one step. And I'm going to let you follow the intermediate steps. Okay? Sorry. I wanted to leave that for practice. But here what I'm saying is, as I write down my sum, there will be a point where I equals 1 and j equals 2. Okay? When I equals 2 and j equals 1, that's flipping the 2. I have to put the minus sign. That's what the epsilon ijk is telling me. So I can see now these two terms will cancel. And if you think about it, when I have the cross product and another derivative around, things are most likely going to have to be 0 because of the fact that this equals that. And so in the one case, it's if I'm taking the cross product of a vector to begin with, when I take the divergence of that is when I get 0. When I take the gradient to make a vector and then take the cross product of that is when I get 0. So those are the two cases you get 0. Any questions? I mean, I know there's a lot of questions. Any more questions you want to ask? Like I said, this is such an important and useful technique. And it's one of those things that goes from incredibly confusing to why did I never understand it as soon as you understand it. So trust me, once you understand it, it'll be like, oh yeah, that all made sense. But I think these are two examples of using index notation that are really confusing until you get how index notation is used and its power. So that's why I gave them to you to contemplate over the next year or two until you see this again.
So does this prove, or is it caused by it doesn't matter which order you take the partial derivative? The fact that it doesn't matter is part of the proof, part of the derivation. Okay. I didn't know if that's like part of how the system was built.
No, it's no. That's separate, right? The fact that partial derivatives can go in order, different order, is just the definition, how you define them, because you can do the limits in either order. And this just uses that. No, this uses that.
Oh, okay.
Yeah, this uses that. It doesn't prove it.
Why do we use limits?
Because it's easier to keep track of. This tensor is defined in terms of keeping track of the indices, and when you're doing that, it's just easier to label your coordinates with 1, 2, 3, 4, because that fundamentally makes sense to sum over. To sum over x, y, z isn't as intuitively obvious. Yeah, so it's more a notational thing than anything else. When you use tensors, you tend to label your coordinates by 1, 2, 3, or 1, 2, 3, 4, or 1, 2, how many ever you have, and worry about what those 4 coordinates are later. Whether they're x, y, z, or r, theta, phi, you just put that in when you're all done. Excellent. So like I said, I think that's a chunk here that's important to see, but you may or may not use it for a year or two.